Now let's go ahead and do some real-world examples. Exponential functions occur a lot in real-world situations, including population growth. So this says in 2000, the world population was about 6.09 billion, and during the next 13 years, the world population increased by about 1.18% each year. Since it says increase, we know that this is growth, so I've gone ahead and written our growth function here for us to reference. We want to write an exponential growth model giving the population y in billions t years after 2000, and then estimate the world population in 2005. So let's go ahead and identify all of our parts and pieces. My a value is going to be the 6.09, remember that's in billions. R is going to be 1.18, or moving the decimal 2 places, 0.0118 as a decimal. And we will eventually plug in a t of 5 years. But first we want to go ahead and write the generic model and then estimate with a t value of 5. So 2005 would be 5 years after 2000. So y is equal to 6.09 times 1 plus r, which is 0.0118. And that's raised to the t power. And then we can simplify this by adding what's in parentheses. And so there is our equation, and now we want to evaluate when t is 5. So let's say that y is equal to 6.09 times 1.0118 raised to the 5th power. And when you put that in your calculator, you should get 6.46 billion as a final answer. This next one, they want us to estimate the year when the world population was 7 billion. So we want y to be 7 and figure out what our t is. So what we're going to do is, if you have a calculator with you, you can use the table in the calculator by putting in this equation into your calculator. Remember that instead of t, use an x, because your calculator is going to get confused if you use a t. Or you can use this same thing in Desmos. So I'm assuming you might not have a calculator in your possession if you are watching this video. So let's go ahead and take a look at Desmos instead. Here we are in Desmos, and I've put in my equation, again using an x instead of t. This graph looks fairly flat from this angle, but if you zoom out, you can see that it does start to rise pretty steeply. And we wanted to know when y was 7, what is our t value, or our x value. And so I went ahead and plotted a second line at y equals 7, and simply look at the intersection, 11.87. If you were doing this on the calculator, you would do second and graph to look at the table and find when the y value is 7, what our x value was, and you would get the same thing, 11.871. And so we're going to go ahead and call that 12 years, because it doesn't make sense to say year 2011.87. So we're going to say 2012. Back over here in our notes, we know that t is about 12, so we can say that the year is 2012 when the population will hit 7 million. This next example is going to show you how to break the equation apart a little bit when it's not written in the format that we're expecting it to be, in order to pull out a rate of growth or decay, in this case decay. The amount in grams, there should be a parentheses there, of the radioactive isotope chromium-51 remaining after t days is y equals a times 0.5 to the t over 28 power, where a is the initial amount in grams. What percent of chromium-51 decays each day? Now we have to be careful here. The first thing you might notice is that we have a b value of 0.5, and you might be tempted to go ahead and plug that into our 1 minus r equals 0.5 and get an r value. However, notice that this is not in the format we're used to seeing it. It has t over 28. And anytime that there's something besides a t here, it's not as simple as that. We are going to need to move the something else, the over 28, out of that exponent in order to be able to truly see what the decay is. So let's talk about this for a minute. If I have t over 28, that's the same thing as 1/28 times t. So I want to go ahead and break that apart because my goal is to separate the 28 or the 1 over 28 from the t. So let's go ahead and rewrite our equation as y is equal to a times 0.5 raised to the 1 over 28 times t power. And now what we're going to do is we're going to use our power of a power property that we learned back in our chapter on rational exponents. And we will say that this is the same thing as 0.5 raised to the 1 over 28 and then the whole thing raised to the t power. Because remember, if we have something raised to a power and then that whole thing is raised to another power, the powers multiply. Well, here are our multiplied powers right here. So we're just doing that in reverse. Now, let's go ahead and evaluate 0.5 raised to the 1 over 28 power, and we'll get a new decimal, 0.9755, and that's raised to the t power. And now we have something in the format we're expecting, an a value, a b value, and a raised to the t power. So now we can see that our b value is 0.9755, and remember that that's equal to 1 minus r for decay. When we solve for r, we'll get 0.0245. So our equation could be rewritten now as y equals a, remember that's where we would plug into the grams, 1 minus 0.0245 raised to the t power. And so we can see that our daily decay is equal to 2.45%.